And we are back, and we are going to do problem set 4 solutions. So we are working with tungsten. Tungsten is W here. It is cubic material. So if we look at our compliance tensor, we're dealing with something with S11, S12, S12, everything else is 0. S12, S11, S12, everything else is 0. S12, S12, S11, everything else is 0. And then the only difference we have here is we have 0, 0, 0, and then S4, S4, 4, and then this is going to be 0, 0, 0, 0, S4, 4, 0, 1, 2, 1, 2, 3, 4, 5, S4, 4. So we're given the stress state. We're asked to write out the full strain tensor. What's the value of the Young's modulus, Poisson's ratio, shear modulus for this material, etc., etc., etc. So I am going to type out my S. This is going to be S cubic. So we have a cubic material, so S11, S12, S12, 1, 2, 3. This will be laborious, but it'll give you some good practice. S11, S12. Actually, let me zoom in here a little bit. For the audience, 0, 0, 0, and S11, actually S12, S12, S11, 1, 2, 3, 1, 2, 3, and then S44, 1, 2, 1, 2, 3, 4, S44, 0, and then 1, 2, 3, 4, 5, because we need a 6x6 matrix, S44. And then we are done. S cubic. So I can now plug in, I know those values for tungsten. So I could do S tung, which is going to be equal to S cubic slash dot. I'm going to say S11 goes to, actually S11 goes to 2.45 times 10 to the minus 12. It's inverse terapascals. We have minus 0.69 times 10 to the minus 12, and we have 6.22 times 10 to the minus 12. And there we go. Oops, I need to do S12 slash goes there, and S44 goes there. And there I see my tungsten matrix essentially. So let's just double check that, make sure we're all good to go. I think we are. So I have my, I'm going to call this sig1. It's going to be equal to 87 minus 37, 18. And then we do 2, 3, so that's going to be minus 6, 68 minus 12 times 10 to the 6. So that's my sig1. I'm going to have my, and then we don't know our epsilon. So I know that my ep1 is going to be equal to S tung dot sig1. So those are my stress values. So that's my full strain tensor. Know that, remember, these are in engineering shear strain. So what's the value of my Young's modulus? So I know that S11. So if I look at S tung 1, if I do 1 over that, that's my Young's modulus. Oops. S tung 1, 1. So that would be my Young's modulus. I know that basically I could solve for S12, so basically S tung 1, 2, so that equal to minus nu divided by, I'm going to call this y tung, divided by y tung, and then solve for nu. That would be my nu, my Poisson's ratio, and my shear modulus is just going to be, I'm going to go ahead and solve basically G tung, which is going to be S tung of 4, and then basically 1 over. There we go. So those are those values. Okay, so I am told, and I'm given this expression, that generally speaking, if I have a cubic material, I could relate the Young's modulus along different crystallographic directions with this equation, where alpha is the direction cosine between my HKL direction, whatever that's asked for, and the 1, 0, 0, 0, 1, 0 in the direction. So using this expression, what's the Young's modulus of tungsten in the 1, 0, 0 direction? So my HKL direction is 1, 0, 0. Alpha is the direction cosine between HKL, i.e. 1, 0, 0, and here. So cosine, what's the angle between them? 0, so that'd be 1. But the rest of these values, direction, or that's the angle between 0, 1, 0 and 1, 0, 0. 90. Cosine of 90, 0. So beta and gamma are dead, and thus everything in here is also dead. And you could kind of show the same thing for these other values. So it's going to be the exact same value expression. So prove using this method and our typical linear algebra rotation approach that we can calculate the Young's modulus along the 1, 1, 0 direction. So what we're saying is that right now my S11 is basically the same along each of these three directions. So we're asked now to figure out what's my Young's modulus around this direction. So this would be equivalent to rotating around my around my 3 axis, a direction counterclockwise by 45 degrees to get to my 1, 1, 0 direction. So let's just calculate it out here. So if I look at my alpha, so alpha is going to be the angle, so the cosine of what angle? Well, it's going to be between my HKL indices, which is 1, 1, 0 and 1, 0, 0. So that's going to be cosine of 45 degrees. Beta, that's also going to be cosine between my 0, 1, 0 and the HKL. That will also be 45. And then what about around 3? That's going to be 90. So gamma is equal to 0 because cosine of 90 is 0. So gamma is dead. This is dead. So let's go ahead. So my solve, my 1 divided by E110 set equal to S11, or actually, oh shoot. This is the annoying part. But I'm just going to do S tongue 1, 1 minus 2 times, let me go over here, 2 times S tongue 1, 1 minus S tongue 1, 2 minus S tongue 4, 4 divided by 2, and then all of that times basically cosine, and that's where you need to be very careful. Cosine of 45 degrees squared times cosine of 45, you have to type in degree squared and solve it, and I get a value that's a little bit different, makes sense, than my value here. So I could do the same exact thing now, but now rotating with my linear algebra approach, what we've learned about in class. So if I want my S prime 1, 1, 0, or if I want my S 1, 1, 0, I'm going to set that equal to T. I'm doing a rotation around my 3 axis. So T, I first need to do T strain, and then I'm going to do the inverse of T stress. So T strain 3 dot my S tongue dot my inverse of T stress 3, and then to the, that's already to the minus 1, slash dot, what's my angle? Theta goes to, it's a 45 degree rotation. So if I do that, if I do my S110, pull out my 1, 1, if I do 1 divided by that, what do you know? The exact same value. Perfect. Write out the stiffness and compliance matrix along the 1, 1, 0 direction. So I already have my stiffness. My compliance is just going to be my inverse of S110. And that is, let's look at it in matrix form. And that would be my compliance matrix. So I could look at it as well here. So if I do S110, S110 slash matrix form. And that is problem 1 done. So let's get on to the next problem with number 2. And we'll use this inverse relationship quite a bit. So this problem is asking us to write out and basically determine the unknown values in our compliance and our stiffness matrices. The key thing that we need to solve for all these problems is S equals C inverse and C equals S inverse. That's really the name of the game, and then identifying what type of material this is. So this material here, and this is not A, this should also be 5. There's a little typo there. This material has 3 unique values here. We have a unique value here. We have basically, if you look at this, 1, 2, 3 unique values. This is a cubic material. So I can go ahead and try to solve for my unknown values. So all I'm going to do is I'm going to do solve, and I'm going to actually do, I could solve this multiple ways. I could just use this relationship, or I could use the fact that if I do S dot C, that's going to give me my identity matrix. I could solve for that as well. But I'm just going to do, I already have my S cubic. I'm going to do basically S cubic slash dot. In my S cubic, my S12 goes to 0.1, and my S44 goes to 0.6, and that's going to be equal to my inverse S cubic, which is basically slash dot. I need to do basically. I need to look at my actually inverse C cubic, inverse S11. I could actually just plug this in. Let's see if I could do this. I'm trying to see if I could do this a little bit the lazy, the lazy person's way. So actually, let's look at inverse. Inverse this cubic. Yeah, we need to. Now I'm gonna have to do it the long way. So let's push through this together, and then we will kind of work out the rest of the solution. C cubic. So I'm going to just change this with all the C. C, 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 C. I guess you could solve it the other way as well, but let's just do it this way. So solve this equals inverse C cubic slash dot. And then for the C, we know that C11 goes to 5, and that's it. Oops, and I think it doesn't. Let's see what my error is giving me here. I think I need to do, I could do this, and what do I want to solve for? I want to solve for S11, C12, C44. What does it not like? Interesting. Does it not like this? Replace all? I know it's, sorry, excuse me. That's good. It's a good little practice for coding, debugging. So when I need to do this, I need to do this. And now I can do this. And so I see my values, and I'm just going to look at real values, but that's fine. So the solution that really would work would be the following here. So I've got my values. That's it. So I can go ahead and I'm going to basically do the same procedure with all the rest of these values, but I can kind of see where we're going to go with this and if I have enough equations. So you can start to see we have a limited number of equations and that we can kind of work with. So let's go ahead and look at this next. What material is this C2? So in C2, I see we have basically all different values here, all different values here, and then different values here, different values here, different values here. So this is orthotropic. So you would do the exact same procedure, and if you follow it out, it's not solvable. So unfortunately. And then when we look at the values here, there's actually a little bit of an error in this. So we see here that we have two of the same Young moduli and then something different. Two of the same moduli, something different, and then all of these values here, these are both the same and then something different here. This looks like it should be transversely isotropic, but if that's the case, then one of these values must be equal, so it's kind of a nil problem as well. So again, that's just what you're working with on problem 2. Now to number 3. So let's look at this standard linear solid model. We said that at basically extremely high strain rates, or i.e. time t equals 0, that we could replace this dash pot with just a straight line. So if that's the case, I have these two, my effective stiffness, E stiff, of the whole system would just be these two wires in series, or in parallel, excuse me. So 1 over E1 plus 1 over E2. At time equals infinity, now it's no longer basically a straight line, but this is basically unconnected. So now when I'm pulling, this guy has no contribution, and my stiffness would just be equal to E1. Now to the fun constitutive relationship that we played around with class. So I see that I have two systems here, two arms basically, or two components. I have this one arm, and then I have this, which is my good old friend, my Maxwell model. So if I go back into my notes and into my discussion of linear viscoelasticity, I can start to go ahead and solve this problem. So whenever you're solving these problems, it's very useful to have handy your linear viscoelastic solutions for the strain rate and your constitutive equations for your Maxwell and your Kelvin-Voigt models. So the constitutive relationships, remember, we need to write everything in terms of our standard linear solid model. So in this scenario, if I break it down into my one arm and my Maxwell arm, I know that when I'm in parallel, my strain in my SLS must be equal to the strain in the Maxwell equal to the strain in my one arm. And thus the stress in my SLS is equal to the stress in my Maxwell plus the stress in my one arm. Now luckily, stress in the one arm is just equal to E1, and then the strain in the one arm, which is equal to the strain in the SLS. So I've already got this for here, right here. Now, how do I write the stress in my Maxwell model? Well, if I look at the stress in the Maxwell, that is equal to my strain, basically eta times my strain rate, and then you have to go back and kind of look at your Maxwell model. Strain rate of my Maxwell model, but that's also equal to the strain rate of my SLS, and then that is going to be minus the stress over my Maxwell over my E2. So, times eta, excuse me, minus E2 times eta. So that is my expression that I could plug in for Maxwell. But now I'm almost there, but I have this problem with, I'm left with this strain dot of my Maxwell. Well, I could rearrange this expression here and write that my strain in my Maxwell is equal to my stress in my, or if I do a strain rate, SLS minus strain rate of my 1. So if I write the strain rate of my 1, strain rate of 1 is just going to be E1 strain rate SLS strain, and that's it. So I can rewrite and basically plug in into this equation. I've got my SLS, I've got this goes into here, and then I could replace this with this expression and this expression here. So I could plug both of these into, where are we at? This strain rate here, and then this guy goes right here, and everything's written in terms of the stress of my standard linear solid, my stress rate of my standard linear solid, and then my strain rate of my standard linear solid, or my stress, or the strain of my standard linear solid. So that's it. Those are those two equations. Now you can just write out the whole mess, but that's how you'd solve for it. So let's do the same one for this next one. So remember, time t equals 0. This is just going to be, this will simply look, once this is stuck, so now this won't move, this won't strain. It's basically, infinite stress. There's no strain in this component, but I'm going to have my, basically the strain here, so it'll look kind of like E2, little, again, but you're going to be kind of constrained here with this, immovable box. Time t equals infinity. This is disconnected. This is disconnected. So you're just basically going to pull, nothing, because we're disconnected there. So there's no stiffness. All right. What about our standard linear solid model? Well, I see that I've got, in series, I've got my Kelvin-Voigt, and I've got my Maxwell again. But now, since they're in series, the strain of my standard linear solid model is going to be equal to the sum of the strain in the Maxwell plus the strain in my Kelvin-Voigt. The stress, however, in my standard linear solid model will be the same as the stress in my Maxwell equals the stress in my Kelvin-Voigt. How do I write the stress or the strain in my Maxwell? Well, I could do the strain rate of my SLS is equal to my strain rate of my Maxwell. We have that previously, and that's just going to be equal to the stress of my Maxwell, which is equal to the stress of the SLS, over my E2, and then plus the stress in my Maxwell, which is equal to the stress in the SLS, over eta 2. So I've got that. That's my strain rate of my Maxwell. But what about the strain rate of my Kelvin, or my Kelvin-Voigt model? How are we going to do that? Well, I've got an expression as well for the strain rate of my Kelvin-Voigt. That's going to be equal to the stress of my Kelvin-Voigt, which is just stress of the SLS, over my eta 1. And then here's the rub, minus E of my 2 over eta of my 2, or excuse me, of my 1. Sorry about that, I was looking at the wrong 1. And now, but I'm also stuck with this strain of the Kelvin void. Not strain rate, excuse me, just this regular strain. So when I plug this expression in, this is completely finished. So I could plug this in right here, right now. I could also plug this in, but I'm still stuck with the strain in the Kelvin void. So again, I'm going to have to rewrite it as strain in the SLS minus strain in the Maxwell equals strain in my Kelvin void. But I don't really have, again, if I try to plug that in, I'm still stuck with this, you know, I don't have an expression for Maxwell in terms of just strain. I need it strain rate. So I'm going to have to take another derivative here, time derivative. So now I could plug in this expression again, not this expression again, but I'm going to have to basically, throughout the whole function, I'm going to have to take, in order to rewrite this expression, I'm going to have to take the derivative of everything here. So now I'm getting a double derivative. So this, you know, basically everything here gets a double, or, you know, a time derivative on it. So this gets a time derivative, that strain rate, or actually basically everything in here got a time derivative on it, because initially that was the, sorry, let me get this, the strain of my Kelvin void, but when I plug it in, I'm gonna have to do that other time derivative on it. So that's the issue. So you're gonna end up with some terms that have double derivatives and other terms that have single derivatives. Excellent. So now let's look at the next question. So I'm gonna erase here. I wish there was like automatic erase all ink. Please do this OneNote. Just let me erase all the ink on the page. There probably is a function, but I just don't know that that is the case. So what type of test is being represented in the following, you know, so let's look at number 5. Look at the plot. What type of test is it? Determine which model best fits the data, determine the constants, fit the data, Young's modulus, viscosity material, what times, blah, 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 blah. Okay, so I'm applying a constant strain. So I have a constant strain that I'm applying, and then I am measuring essentially the stress. So this is basically an example of stress relaxation. So this is stress relaxation. We have this, our epsilon naught is equal to 0.001, and then I am measuring a stress relaxation. So the models that we've worked with, if I look at the Maxwell model, I have, essentially, if I look at the strain rate, I have this exponential decay. If I look at the Kelvin void model, it just looks like a linear function, E naught, which is not the case. So my function is the Maxwell model, so this is looking at the stress relaxation of the Maxwell model, and that is equal to sigma naught exponential of minus t over tau, where tau, again, is equal to eta over e. And we also know that when we apply sigma naught is equal to e epsilon naught. From our strain, if you look at that Maxwell model, again, for very, very short times, our Maxwell model basically looks like this. It's just going to be represented by E2. So we can make this approximation. So if I look at time t equals 0, my epsilon naught is just going to be this. So I see my epsilon naught, this is equal to 1 times 10 to the 6 pascals. So now I can start solving and cooking and basically solving for some of these unknown values. So I'm going to solve that. My E naught, so I'm just going to say E naught is equal to 0.001. I believe that is correct. Yes, it is. My sig naught is equal to 1 times 10 to the 6. So now I could solve basically sig naught equals y times E naught. Solve. So this is my Young's modulus. What do you know? It looks like a polymer. So y, I'm going to call this y of, what problem is this? Problem 5, I believe. So y5 equals this times 1 times 10 to the 9th. So that is my Young's modulus. So I've got that value now. So I've got sigma naught. I've got my E here. So now I can start to kind of read off, okay, like for example, and this can be a crude approximation, but let's just say that at I read a value of that my stress, so solve So 200, equals my sigma times exponential minus time is going to be what? 0.0. Let me erase here quickly. Erase 0.002 seconds. So time is 0.002, and then divided by my, basically, my tau, remember, is going to be equal to my eta divided by my y5. And then I'm going to solve for my eta. Again, this is a crude approximation, but something, again, you could probably do a nonlinear fit, learn about that in my new course coming up this next spring. So there's my eta. So what is tau is equal to eta 5 divided by my y5. So this is pretty small. So it's less than 0.01. So remember, we had tau is essentially equivalent to our Deborah number. So dE, our Deborah number, which determines whether a material is solid or, our Deborah number is equal, basically is equal to our tau star relaxation time of polymer over time. So if my relaxation time is incredibly small, then we should know that our polymer, so if our Deborah number is really small, I mean less than 0.01, that polymer, that relaxation time is incredibly small relative to the experimental time. So that will behave essentially like a liquid. If it's greater than 1, so basically if the Deborah number is less than 0.1, this is going to be liquid. If the Deborah number is greater than 10, it's going to be solid, in between there, viscoelastic. So this polymer, again, depending on the experimental times, will most likely kind of look like, well, it actually depends on the experimental time. So we can actually solve. So let's solve, so 0.1 equals tau divided by t. So if our experimental times are less than this, it will behave, or basically this, or basically longer. So actually, let's look at tau divided by 5. Yeah, if it's this time or longer, it will be acting like a fluid. If it's this time or less, actually let's do it for the 10. If it's this time or less, it'll behave like a solid. In between those two times, it's going to behave like a viscoelastic fluid. That's it. So below is an experiment of the dynamic mechanical testing that has an x-axis cut off. One material is polypropylene, which basically is, if you look at this, it has, basically you can look at these structures. So polypropylene, if you look at the, actually let's go ahead and look at each of these. I'm looking at this. So chemical structure, polypropylene. So we could kind of look at these. It has that methyl group, and then what are the other polymers we're looking at here? So polypropylene, polycarbonate, chemical structure, carbonate, chemical structure of nylon 6,6, although I can draw that one. Nylon 6,6, and then chemical structure of PDMS, polydimethyl siloxane, and the chemical structure of polysulfone. So we'll come back to these in a little bit. So the first question is asking us, what is, if we were to plot essentially our x-axis in terms of frequency times or temperature, what would it look like? So remember, this is our storage modulus, where we need to be, where basically here, if we kind of cut off, this is where we should be behaving elastic, and then this should be our viscous response. So we are elastic at temperatures that are very low, strain rates that are very high, and time that is essentially very low, effectively. Viscoelasticity, on the other hand, temperatures that are very high, strain rates that are very low, long, and times that are very high. So, and then you can kind of do the same thing for frequencies that are very low, frequencies that are very high, and frequencies that are very low here. So the problem is then asking us to, okay, draw how these And this kind of crossover point, that is our characteristic relaxation time, tau. So this would be the tau for polypropylene. So if I look at these other polymers, polycarbonate, nylon 66, polysulfone, so if I look at polypropylene, this has a CH3 in it. If I look at polycarbonate, it's got these nasty, super, super rigid backbones, possible H bonding going on here. You could also see, depending on some of the structures, it's got this methyl HCH3 groups as well, so the methyl groups. Nylon 66, we have H bonding. If I look at PDMS, this is probably our lowest TG. So the lower the TG, the faster the relaxation time. So it has a very, very, very fast, so again, our relaxation time is going to be, our relaxation frequency is 1 over, let me see what's being asked here. So yeah, it depends on your axis. So if we were drawing, essentially an axis where we're looking at this relaxation time, so the relaxation time is going to be proportional, actually going to be inversely, proportional to the TG. The lower the TG, the lower the relaxation time, the faster it's able to respond. So my tau of my PDMS is going to be probably the lowest. So this is less than the tau of my polypropylene will be probably next. Then I'd say probably the tau of my nylon 66. Then I'd say probably like the tau of my polycarbonate, just to do that rigidity, and then the tau of my polysulfonene. The polysulfonene is a really, where's polysulfonene? It's really kind of disgusting. Look at all, that's methyl groups, double bond, yeah, it's a big mess. So that's how essentially that pot would look. So our relaxation time of polysulfone would be way over here, and then the relaxation time of PDMS would be way over here. So that's it. Now, let's get to the last two quantitative questions and all of these good rotation matrices, and let's kind of figure this out. So let me go ahead, and I'm going to, actually, we won't erase, let's just start mathematic on this one. So let's go ahead. So now on to problem 7. So I have the full stress state in a certain coordinate system. I also have the full strain, or actually not the full strain state, but let's see what that is in just a minute. And then I'm given the Young's moduli in 3 different directions. It looks like I have an orthotropic material, so I'm going to go ahead and write out S ortho equals S11, S12, S13, and then 1, 2, 3. And then let's go ahead and close that. S12, S22, S23, 1, 2, 3. And then I got S13, S23, and then S33. And then that's going to be equal to 1, 2, 3. And let's go ahead and continue. I've got 1, 2, 3, and then S44. 1, 2, 3, 4, S55. And then I've got 1, 2, 3, 4, 5, S66. So that's my ortho in the original coordinate system. So I'm given that, I'm given the stress strain values, and I'm asked to write it for these rotations as well. So let's go ahead and write out that my sig, we call this sig 7, is equal to, again, this is on 58 minus 76, 98. I'm going to do 2, 3, which is 36, then 1, 3, which is 18, and then this is the 0. And then times 10 to the 6. And then in terms of I need to be careful here now because I'm given the values in this tensor notation. So strain 7 is equal to 0.06 minus 0.01384, 0.02206. And then now when I do the 2, 3, 0.003 times 2, because I need to work with engineering shear strain, 0.00225 times 2, and then this is my unknown E12, or gamma 12. So I'm also given in this S ortho slash dot, basically, I'm also given, if I look at this, my E11 is equal to 1 times 10 to the 9. My E22 is equal to 5 times less than that. So, excuse me. So E11 oh, actually, sorry, excuse me, E11, which is 1 gigapascal, which is 10 times less than the 22. So E22 equals 10 times E11. And then E33 is equal to 5 times, which is 111 is 5 times less than 3 in the 33 direction. So 5 times E11. So I got those values, and now I can substitute in here. I know that my S11 set it equal to 1 divided by E11, S22 set it equal to 1 divided by E22, and S33 set it equal to 1 divided by E33. And we could kind of plug that in here. Let's look at this numerically. Full simplify, just making sure everything is nice, sweet and easy. Great. So now I'm left with quite a few unknowns. So I don't know what S12 is. I don't know what S13 is. I don't know what S212, 13. I don't know what 23 is, and then S44, S55, and S66. So one of the nice things that I can do is I could start doing strain 7. So for example, I could pull out the 6 and then set that equal to S ortho dot sig 7, and I could do basically pull out the sixth equation. So now I see that gamma 12 is equal to, actually should be equal to S ortho. We should have S66 there. So actually let's pull out this equation. I think it's already doing the 0 times this. So in general, where's the gamma 12? So what about, I think it's already, I think even if I do that here, yeah, it's already set this equal to 0. So anyways, we know that basically, actually, well, it gives us this right here. We know that S66, it exists, but we don't see any strain there, so we know that our gamma 12 must be equal to 0. So I can start to basically set that equal. So I got this is equal to 0. So that's one basically given. So I could solve now for 5, for example. So I have an equation here that directly relates to S55, so I could solve this. Solve for S55. So I've got S55. So S55 is equal to this. So I could do the same thing for S44. I'm just pulling out the 4th equation because these give me nice, you know, basically linear equation. I don't want S55, I want S44. S44 is equal to this. Like that. And now I've started to fill out this, you know, quite a bit. So I still don't know what S66 is. Now I need to figure out, okay, I've got 1, 2, and 3 unknowns. But luckily, if I look at my S ortho dot S dot sig 7, I've got 1, 2, and 3 equations here that lead me to my 3 unknowns. So I could solve this for S12, S13, S23. Can I solve all those? Oh, I need to set this equal to sig, or strain, what did I call it? Strain 7. And what do you know? Pretty straightforward, nice and easy, got my answers. So now I could go and start to solve. So I know this is equal to this. Now, how am I gonna solve for this, my last one? Let's go here, let's go here. So now I'm starting to solve for basically everything in here. So how am I going to solve for this last value? Well, the problem is telling me that I also need to figure out or write out the full stress and strain tensors and full compliance matrices, the units, all those good things. I need to do a rotation around the 2 axis of 76 counterclockwise. So I'm going to do my S ortho 76 is going to be equal to T stress, or T strain 2 dot S ortho dot T dot the inverse of T stress 2 slash dot theta goes to, what was the angle here? 76 clockwise, that's minus 76. And let's just go up and make sure that this, whenever we're doing the primes, yeah, strain and then inverse stress. Got that. Oops. What does it? Let's look at this numerically. Ooh. T strain 2 dot inverse. I think I may have made a mistake somewhere. Let's look at my ortho should be fine. So let's go ahead, whenever you're debugging this, so let's go ahead and look at like T stress 2, T strain 2. So let's look at dimensions T stress 2. It should be a 6x6. So dimensions T strain 2. Let's look at the dimensions of S ortho. So see, there's something wrong in here. So 1, 2, 3, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3. 1, 2, 3, 4, 5, 6. The comma. And the same thing here, most likely. So now if I look at this, I got 6x6, 6x6. And now I can start to go. And let's go ahead and type this up. Now we've got our values. And we can see here, I'm also going to have to do the same thing. So my S7 stress 7P, my prime, is going to be equal to T strain 2, actually T stress 2 dot, what do I call it? I call it sig 7. Dot sig 7 slash dot theta goes to minus 76. So that's my new stresses. Let's look at this numerically. I can also figure out my new strains. Strain 7P is equal to T strain 2 strain 7. So now I can see here in my last equation here, so if I look at my S ortho 76, for example, if I look at my 6 and I look at my 6th equation, oops. So now I could do solve. Actually, let me do it. I could do actually this. So I'm going to do S ortho 76 dot my stress 7P. So I want to look at the 6th equation here. I'm going to go ahead and solve. Oops. Let me pull this out here. Sorry about that. What does it not like here? Let's pull this out. Actually, let me look at here. Do full simplify. Oh, that's what it is. Oh, that's why it's not giving me a value, because it's already, that is a little bit. So my equation, this is a little interesting. So let's look at S ortho period. So let's do full simplify, oops. So where do I have, well, that makes, oh, actually, did I define, where is S66? Should be in here. S66. So if I look at my stress 7p, now I still have that. Let's look at my strain 7p. I definitely have a strain there, so something a little bit funky is going on here. This is giving me this value here. Let's see if this matches our strain 7p. It does match, so it looks like what's happening here is that we're canceling out. We're not being able to solve, essentially, for this S66 here, which is a little bit unfortunate. But so that's around the 2 axis here. So what if we rotated around, let's just say the 3 axis? Then we wouldn't have the relationship. We could figure out, let's say we rotate around the 3. Then let's do stress 3, 3. There we go. I think that there could be an issue with I have a feeling there might be an issue with my tensor up here. Let's look at this T stress and T strain just to double check in that 2 direction. Let's see. In the 2, we should have C squared, S squared for stress, minus 2SC, 0, 1, 0, S squared, S squared, comma 0, C squared, 2SC. No, this is looking pretty good. S times C squared minus S squared. 0, 0, 0, minus S, 0, C. Let's look at strain. C squared, S squared, minus S times C. 0, 1, 0, S squared, C squared. S times C, 0, 0, 0, CS. 2SC, minus 2SC, 0, C squared, then minus S minus C. Yeah, no, that's correct. So it's probably just an unfortunate coincidence. But anyways, so I could do the same thing. I could do for the 3 though, the 3 axis, and I can clearly see here that I will have an equation. And actually I could look up, I could just pull out, for example, the 6th, or actually I'll just do this. Solve strain 7p set equal to S ortho 76 dot stress 7p for S66. Yeah. Doesn't want me to do that. What I could do, just pull that out for S66. Yeah, let's see what the problem is here. So that should be solvable. Strain of 7p. Should be able to. Let's see, 5, 4, 3. Let's look at 2. So let's see, here we go. Sometimes Mathematica just doesn't like to solve for these values. So let's set it equal. So now let's look at S ortho. So let's see, symmetric here, symmetric there. Excellent. Now let's go ahead and look it up here. All right, then let's look at S ortho 7, 6. Let's look at it. So now we've got let's zoom out a little bit. Sorry about that, but it's good to kind of look at the solutions. Here, symmetric, here, symmetric, here, symmetric, there. Then we have essentially these couple of interesting values here. So this symmetric here, this symmetric here, this symmetric here, and then we see symmetric across here, and then the unique values across there. That's it. So you see these kind of weird off-diagonal components that start to come up once you start to rotate. So you're getting these, again, here we're getting basically shear strains from normal stresses. So that's a little bit strange, but that's what happens when you rotate these unique values. All right, on to the last problem. So in this last problem, we are given this is a composite type problem. So I'm going to go ahead and draw a little bit here. So we're given a coordinate system 1, 2, 3, and essentially in our original coordinate system, the way we want to mash home runs is I want my fibers pointing basically along this 2 directions. So I want my fibers pointing like this. So basically it means my E22 is my greatest, and then E11 is equal to E33. So basically I'm going to have unique values, or basically similar values in the 1, 3 plane, as we're going to see in a second, and then anything that has the 2 in it is going to be kind of unique and distinct. So E22 is equal to E of my fiber, fraction of fiber, plus E of my matrix, fraction of matrix, and then E11 is going to be equal to 1 over the basically fraction fiber over E of my fiber plus fraction of matrix over E of my matrix, and I need to make sure my fraction, F fractions go from 0 to 1. So that's one of the key things. So initially, I'm given all of these values. I can assume everything else is 0 when I am in this kind of weird coordinate system where basically from where I want my fibers to be, they're rotated counterclockwise 28 degrees. So I can go ahead and start to solve, or at least set up this problem. So I'm going to say that E of my fiber in this particular problem is equal to 950. 50 times 10 to the 9. E of my matrix is equal to, what, 25 times 10 to the 9. Let's make sure that's correct. Yep. My fraction of fiber is equal to 0.1. My fraction of the matrix equals 0.9. So my basically E2 is going to be equal to, actually this is the part where I should probably, I'm going to quit my kernel because it's getting a little bit dicey. And I think that was actually maybe what was wrong with the other problem. Great. So now I can go ahead, E2 is equal to E of my fiber times fraction of fiber plus fraction of matrix times E of the matrix. And I could do that E1 is equal to basically 1 divided by fraction of fiber divided by E of fiber plus fraction of matrix divided by E of my matrix. And then E3 equals E1. All right, and then my S, because I'm transversely isotropic, S iso in the original coordinate system is going to be equal to S11. This here is the danger. So S12, and then I need to think about if my properties are the same or if my properties are different in essentially the 1, 3 direction. So when I'm looking at a transversely isotropic material, we say in the 2 direction we have kind of those components. So when I'm looking at my setup, I know that my S11 is going to be equal to my S33, and my S22 is right here, where my S11 is equal to 1 over E1 equals 1 over E3 equals S33. Now, I'm going to have an S12. So that's describing essentially the properties in that 1, 2 plane. In the 1, 3 plane, basically, if I'm looking at the 1, 3 plane and I'm looking at kind of like the translation there, I am basically I'm not touching any fiber direction. So that is going to be distinct as well. But the rest of the values in the S, so this will be S12, in the 2, 3, those are going to act the same as in the 1, 2. Because I have one direction that's along with fiber and one direction that's also. So this is going to be actually S12, S12, and the same thing for here. My S44, that refers to the 2, 3 plane. my S55, that corresponds to the 1-3 plane. So this is going to be unique. S66 is the 1-2 plane. So anything that has a 2 into it, that is going to be essentially behaving the same. So my S44, S55, S44. So that's the key distinction there. So S13, 1, 2, 3, S12, S22, S basically 1, 2, 1, 2, 3, because it's the 2, 3, and then S13, S12, S3, actually S11, 1, 2, 3, then 1, 2, 3, S44, 2, 1, 2, 3, 4, S55, 1, 1, 2, 3, 4, 5, comma S44. Let me make sure that that looks correct. It is. And S-iso, isotropic. So S-iso matrix n slash s full simplify slash matrix form. Great. So I'm symmetric, I'm looking good, and then now I could go ahead and start to solve. So I'm going to also set slash dot basically S11 goes to 1 divided by E1, and S22 goes to S1 divided by E2. There. All right, so now I'm starting to click with gasoline. So let's look, and then I'm also given essentially some values in the, so this is my S stress 28. So let's go ahead and pull back here. So my stress in the 28 is equal to 10, 58, 1, 2, and then 100. So all times 10 to the 6. I could assume the rest of those values are 0. My strain in the 28 is equal to 0.23677 minus 0.0034. 1, 2, 3. So 1, 2, 3, 4, 5, 6. Yep. And now again, I got to be careful about, but luckily I'm already given these values, 0.0476. So there we go. So that's my strain, and then again, we are in the 1-2 plane. So if we need to rotate, we're going to rotate around that axis. So let's see again what we need to rotate back. So my stress OG is going to be equal to T stress 3 dot stress 28, and we're going to rotate clockwise 28 degrees slash dot theta goes to minus 28. Let's look at this numerically. I'm going to do the same thing here. So strain OG equals T strain 3 strain 28. So those are my values. So now I can start to solve. So I'm just going to look at, again, but I need to also rotate my, so this is in the original coordinate system, i.e. S-iso. So if I do S-iso dot stress OG, I could start to see the equations. So I'm going to do full simplify. So I see I have an equation with S12, 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 S13, and S14. So let's see if I can be lucky and solve the S. Actually, I think I can just do this. Solve strain OG set equal to S-iso dot stress OG, and then S12, S13, S44. And it doesn't like it for some reason. And again, sometimes Mathematica, it'll give you a little bit of annoying. So let's look at what this gives us. Actually, we know what that gives us. What about strain OG? We know what that gives us as well. So maybe it wants me to put it as a series of equations because it is kind of like that. Or I could start to look at solve, but so basically it's saying that it's not solvable. Well, that's not the case. So, but I could actually start to kind of solve this myself. So again, I could look at, for example, my 6 component. I could look at this equation So for example, here, I can look at the 6th equation here. So I can look at this. So I could get my S44. So I could get that value. And then I could start to kind of play around with the other values. So let's look, for example, at, let's look at equation 1 here. So here I'm given equation 1, but only one answer solution there. I could also be given equation 2. So I could try to ask to solve for these simultaneously. Let's see if this, but it might give me the same strange S12, S13. That's why it doesn't like the, so let's see, 1, 1, 2, 2. Solve for S12. Actually, if I look at these equations, just solve them simultaneously. So I could get S12, solve that value, and then I could also now solve for the third, S13. I could get that value right here. So let's look at our S iso. So let's look at the full, actually, matrix form. So I still need the S55. So what am I going to do? And actually, if I look at my, I could also look at my S28 is equal to T stress, T strain 3 dot S iso dot T stress, or T actually inverse T stress 3, and that's going from slash dot theta goes to, it's the 28 now. So we're going from old coordinate system to the new coordinate, to that rotated one. So just and we'll simplify. So I could see, actually we could look at this S28. Matrix form. So I could see it's in these off-diagonal components here that are giving us the equations. So we could do stress, actually S28 dot stress 28. But we see here, unfortunately, because I think our interesting equations, well, actually we know that that's not giving us anything. So we don't have any equations that give us any values in here. So what we may start to play around with is to solve for S55 to complete the problem again, but you start to kind of see how you can, go about solving these, systems of equations. We can now go about, actually, we can absolutely now go about starting to solve and starting to put these equations together. So how can I get the S55? Well, let's go ahead and let's see, what if I rotated stress, let's do stress 28, and let's say then I rotated that like, basically, say I rotate around the 1 axis, just D stress 1 dot this slash dot theta goes to 35 degrees, who knows? What does it look like? I think I had the same problem with my T stress 1. So let me go to my T stress 1. Where are we at? Yeah, look at this. 1, 2, 3, 4, 5. So let's look at the T stress 1. I think there's a little error right there. We caught it. T stress 1 is going to be this 0 minus S times C. There we go. S times C is great. There we go. And I'm going to do the same thing right here where it turns to 2. And then now it'll be okay. So if I look at this, T stress 1. So now I have all my stress values. so this is going to be my stress 1. Basically stress 1 rotation. I could do the same thing for, actually, here we go, let's do strain 1, T, and then I could also do my S28 or T1, T strain 1 dot S28, because that was my coordinate system there, dot with S dot inverse T stress 1 slash dot theta. So I could just do an arbitrary rotation to get to the values that I need to look at. So do I have any S55s? Yes, I do. Hopefully I have an equation. I mean, they're pretty much all over the place. So let's just look at, for example, 6. So this is my S1. So S1, actually let's do S1 dot stress 1. Yep, so let's look at our number 6 equation. And let's there we go. So you can get some value. Again, it's probably nonsensical at this point, but so now I can look at S1. Oof, that's a nasty. See, that's a nasty S28. I've got that, and then I got my S. And you can see I'm all symmetric each time. S iso. So again, it's all about setting up these systems equations and then solving. So hope you've enjoyed it. That is the problem set, and have a good one. Thanks. Bye.